All right, so in this example, we are looking at children's weights. So we have our question that is really, anytime you have a question in these things, it's probably going to inform you about the alternate hypothesis, right? So we have our kids heavier now than they were in the past. So we think maybe because of, whatever reasons, sedentary lifestyle, worse eating, more time on screens, less time outside, whatever, we think maybe kids weigh more than they used to, right? Okay, so we have the National Health and Nutrition Examination Survey taken between 1999 and 2002, reported the mean height of 6-year-old girls in the U.S. was 49.3 pounds. I don't like the green. Let's go. I guess we'll go for orange. All right. Now, so another survey from 2008, so, about 8-ish years later, reported that a sample of 193 6-year-old girls weighed in 2008 had a mean weight of 51.5. We are told to assume the population standard deviation is 15 pounds. All right, so let's start by writing everything that we know, right? That first off, we can ask this question first, right? Are we dealing with means or proportions, right? And this one, again, very, very clear because we know we're dealing with a quantitative variable, weight, and it has the word mean in it, plus standard deviation, right? So we know we are dealing with means. Great. Do we have a sample size? Yes, we do. Sample of 193 people. Do we have a sample mean? Yes, we do, right? The sample had a mean weight of 51.5 pounds. Okay. Now it says assume the population standard deviation is 15 pounds. So you got to ask yourself, is that S, the sample standard deviation, or sigma, the population standard deviation? Well, it says the words population standard deviation, so this is sigma, right? So, and that leads us, this is a good time for us to say, I know I'm doing means, so do I do Z or do I do T, right? And the question that we ask there is, do I know sigma? I do know sigma. Therefore, I'm going to do a Z test, right? So we are going to use Z. Okay. All right. We have one more number in here. We have that 49.3. That is what used to be true, right? So this is going to inform our null hypothesis, right? Because null hypothesis is a statement of no difference, no change. Our kids' average weight has not changed since the 1990 to 2002 survey data, right? And we're assuming, that's a national thing. We're taking that as a population number, right? So our null is going to be mu equal to 49.3 pounds. Right? Our kids are no different than they were 8 years prior to this problem setting. But our alternate, we think they weigh more, right? So our alternate is going to look exactly the same parameter, mu, right? We are testing the population mean, mu, right? Same value, 49.3, what it used to be in the past, but different symbol because we think kids weigh more now. So it's going to be a greater than. If we had said, hey, we think kids weigh less, we would use a less than. Okay. So now, before we go here, it's a good idea to make a sketch, right? So I'm just going to label. So we have our claimed mean, 49.3, our sample mean, 51.5, and again, we are shading to the right because we're shading the greater than side, right? Okay, so that's what we expect our p-value to look like when we do that. And we should also check conditions. Now, this is a government survey, and again, they've got statisticians working for them, so they should know that the sample needs to be random, Okay, so we're going to assume that it is, even though it doesn't say so. But again, because this is a professional, basically a bunch of statisticians taking it, they know what they're doing. So we're going to assume that yes, it's random. Do we know if the population is normally distributed? Maybe, maybe not. It doesn't really matter because our sample size, is bigger than 30 because it is 193. So we're good there, right? But we're still less than 10% of the population. That is fine because there's definitely more than 1,930 6-year-old girls in the country. That's definitely done. All right, so we need to do our test statistic. Now, we already decided that we were doing a z-score. I'm going to go change colors. We remember that that is x bar minus mu over sigma over root n for our means. So now we just need to plug and chug, right? X bar 51.5. Our hypothesized population mean 49.3. Our population standard deviation 15, and our sample size 193. So we're going to go throw that into GeoGebra calculator. Hopefully I can remember all those numbers, right? 51.5 was our sample mean. 49.3 was our population mean. Standard deviation was 15 over the square root of the sample size 193. So our z-score 2.0375, or you could say 2.038, or you could really even go for 2.04. But let's say 2.0375, because why not? Okay, 2.0375. So we're pretty far out there, but not as far as some of our previous examples. Okay, so that's our test statistic. Remember, test statistic is a general term for me to say, hey, what's your z-score? Or maybe it's a t-score. You have to figure it out. Okay, so we need to figure out our p-value. Our probability of getting a sample mean greater than, or at least, 51.5 pounds. We're going to have to go to GeoGebra for that, right? Or your z-table, or a calculator, right? Make sure that you're on normal distribution. And right-tailed again, and we were at 2.0. I've already forgotten. I hate that little pop-up. Right, 2.0375. Okay, 2.0375. Come on, there we go. 2.0375, not 275, 375. There we go. Okay. So our p-value, 0.0208. 0.0208. Great. 0.0208. So we had our test statistic. Now we have our p-value. Seems to match our sketch and our conclusion. All right, now here, I didn't give you an alpha level. we're going to run this with 2 different alpha levels. All right. So let's assume first a typical alpha level of 5%, right? 0.05. Our p-value is less than 0.05, right? 0.02 is less than 0.05. That means it's too unusual. It's about a 2% chance of happening if the mean is actually 49.3. We are going to reject the null, right? Our p-value is less than alpha. So p-value less than alpha, so we will reject the null. So remember, we need 2 sentences. We need that decision, reject the null or fail to reject the null, and then what does it mean? We can say there is evidence, there is strong evidence that mean weight of children has increased. So I'm going to say that, strong evidence that. And really what we're doing is we're taking our alternate hypothesis and putting it into words, right? And the mean weight of 6-year-olds has has increased. We don't know by about how much, but we know it's gone up. Okay. Now I said I was going to do a second one, right? So let's do that in purple. We're going to do that up at the top because I kind of don't have a lot of space. All right. Now, what if our significance level had been 1%, which of course is 0.01. Now our p-value is bigger than our alpha level, right? Our p-value is 0.02. Our p-value is greater than 1%. So what do we do then? We fail to reject the null. We can't do it, okay? And in this case, we are going to say there's not enough evidence. So we're not going to say that the kids are still, that the average weight is still 49.3. Okay, we haven't proven that. We've just failed to disprove it, which is a little bit weird. And we're going to talk more about that later. But so in this case, we're gonna basically say there's not enough evidence to say the alternate is true. Okay, that's what I'm not gonna write it like that. I'm gonna say there is insufficient, i.e. not enough evidence to say the mean weight has increased. And I'm kind of being short here because I don't have a lot of space. Okay, there's insufficient evidence. I'm going to highlight that, make sure we're on the right color. Insufficient evidence to say mean weight has increased, right? And so that mean weight has increased. That's the same wording in both, whether we're rejecting the null or failing to reject the null. And if we didn't reject the null, then we're saying there's not enough evidence to say the alternate is the case. If we rejected the null, we're saying, yeah, there's evidence to say the alternate is true. But we have to put it in words. All right, that's it for this one.